Hi everybody. For this lesson we're going to take a look at a couple more theorems that we can use to prove that two triangles are similar. In one of the previous videos we looked at the angle similarity, which was the one that said that if two angles in one triangle are similar to two angles of another triangle, then that's enough to say that the two triangles are similar. Today, what we're going to take a look at is the SAS similarity and the SSS similarity theorems. And these are going to be helpful for us if we're trying to prove that two triangles are similar. So let's go ahead and take a look at the first one. So the first one is called the SAS similarity theorem. And what it says is that if an angle of one triangle is congruent to an angle of another triangle, and the sides, including those angles, are proportional, then the triangles will be similar. And so what we're looking at here is a pair of congruent angles, and the including sides are going to be proportional. Now remember, including would mean including sides, or they would be the sides that are on either side of that angle. So if we're looking at angle A right here, congruent to angle R, then the sides that include angle A would be segment AB and segment AC. The sides that include angle R would be RT and RS. And so what the SAS similarity theorem would say is that in this diagram over here, if angle A were congruent to angle R, okay, so that's an angle of one triangle congruent to an angle of another triangle part, and if segment AB over segment RT, in other words, a ratio comparing this segment to this segment, if that ratio is equal to a ratio comparing segment AC's length with segment RS's length, if those ratios were equal, in other words, if the including sides for the angles A and R are proportional, then that wouldn't be enough for us to say that triangle ABC is similar to triangle RTS. So that's SAS similarity. One pair of angles congruent, the sides including those angles will be proportional. So we can set up a ratio with one pair of corresponding sides, and that will equal the ratio of the other pair of corresponding sides. The second similarity theorem we're learning in this lesson is called SSS similarity, and it's a lot shorter because it only involves sides. We don't have to know anything about angles in the SSS similarity theorem. All it says is if the sides of two triangles are proportional, then the triangles are similar. So, like I said, don't need anything about angles for this one. What we need to know is that we should be able to make out three ratios of corresponding side lengths that will all be equal. And if that's the case, then the triangles would be similar. So we would have segment AB, for this diagram over here, it would be segment AB in a ratio with segment RT's length. That would need to equal segment AC's length over segment RS's length. And that would need to equal segment BC's length over segment ST's length. So we have all three pairs of sides equaling each other in a ratio. All three pairs of corresponding sides have the same ratio. And if that's the case, then triangle ABC would be similar to triangle RTS. So we have side angle side similarity and side 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 similarity. So let's take a look at some examples and try and put these to use. So in example 1 that I have here, it says the measures of the sides of triangle HAT are 4, 5, and 7. The measures of the sides of triangle PIN are 16, 20, and 28. Are the two triangles similar? So first, let's do a quick little sketch. It doesn't have to be a perfect sketch, but we just want to sketch out these two triangles and put the side lengths on them. Sometimes this just helps to get an idea of what sides might be matched up with one another. So there's triangle HAT with its side lengths of 4, 5, and 7. Next up we need triangle PIN with its side lengths of 16, 20, and 28. That's 16, 20, and 28. So, since we don't know anything about angles between these two triangles, the SAS similarity theorem would probably not apply here. But we do know the side lengths of all three sides of both triangles. And so as you're going to learn, that means your first thought should be checking if SSS similarity works. And the way we're going to check that is we're going to set up the three ratios of the corresponding sides, and we're going to check, are they all equal? And so first we're going to take, now how do we know which sides might correspond to which over here? Well, we're going to look for the shortest pair of sides. So the shortest side of HAT is 4, and we're going to match it up with the shortest side of PIN, which is 16. Then we'll maybe match up the longest two sides. So that would be a 7 for the longest side of triangle HAT, matched up with a 28 for the longest side of triangle PIN. And then the other two sides would go for our middle ratio here. So that's a side length of 5 with a side length of 20. And like I said, now we're going to check, are those ratios all equal to one another? And there's a couple different ways you could check these ratios. What you could do is you could cross multiply each possible pair of ratios. So you could cross multiply this pair right here, see if they come out, if the cross multiplication gives you the same thing. Then check this pair of ratios right here. And lastly, you'd have to check the first ratio with the last ratio, doing the cross multiplication, see if it all comes out equal. Sometimes that might feel like it's going to be faster for some problems. Other problems, what you can do is just look and see, are they easily reduced ratios? And in this case, you might notice that they are actually pretty easy to reduce. If I start out with 4 over 16, and I try to reduce that, I'll notice that both 4 and 16 are divisible by 4 itself. So for this one, I'm going to divide both by 4. And 4 divided by 4 is going to give me a 1. 16 divided by 4 is going to give me a 4. So that ratio turned into 1 over 4. For 5 over 20, I'll notice that I can divide both of them by 5. 5 divided by 5 is a 1. 20 divided by 5 is a 4. So far, so good. We have two ratios that reduce down to 1 over 4. For the third one, I notice that I can divide top and bottom by 7. 7 divided by 7 is a 1, and 28 divided by 7 is a 4. So I had a 1/4, a 1/4, and a 1/4. So the side lengths between these two triangles are in fact proportional. They all, when I set up the ratios of the corresponding sides, they all reduce down to the same ratio of 1 over 4. So we would say yes, triangle HAT is similar to triangle PIN by side, side, side similarity. And so there's an application of side, side, side similarity that worked. Let's take a look at example 2. Now I did notice before I started this video that I had a mistake that I probably need to correct, because this problem describes a triangle ABC that is impossible because the 5s and the 6 don't add up to be greater than this side of 23. And so we can fix it real quick. We can just make this, give a black pen so it blends in pretty nice. We can make this a 15 and we'll make this a 16. Instead of 5 and 6, it'll be 15 and 16. So then what we want to do is we want to try and check, since I don't have anything about angle measures here, I want to maybe check side, side, side similarity again. First, let's sketch out our two triangles. Triangle ABC. My triangle here doesn't have very straight sides, but you get the idea. It doesn't have to look perfect. So triangle ABC has a side length of 23 for AB, a side length of 15 for AC, and a side length of 16 for BC. So those are my three sides of triangle ABC, and I'm checking, is it similar to triangle XYZ, which we can sketch out right here, XYZ, where segment XY is 2.5, segment YZ has a length of 2, and segment XZ has a length of 3. And again, we don't know anything about angles, so we're not going to be checking side or angle similarity, but since we know all 6 side lengths between these two triangles, we can check side similarity. So what we're going to do is set up our 3 ratios of corresponding sides and check, are they equal to each other. So again, I'm going to pick out, well, in this case, it does give me a specific similarity that I'm supposed to check. So instead of picking out smallest with smallest, I'm going to pair up the corresponding sides according to the similarity statement. So that would be segment AB paired up with segment XY because they're the first 2 letters of each triangle's name in the similarity statement. So segment AB has a length of 23, segment XY has a length of 2.5. Next, I'll pair up BC with YZ. BC had a length of 16, and YZ had a length of 2. Next up, I'm going to pair up the last pair of corresponding sides, which was AC, first letter and last letter. So put AC up there with XZ down here. So 15 over 3. And now I just need to check, are these ratios all equal? Now this one has a decimal in its ratio, so I'm going to kind of save it for last. I'm going to come down here, and I'm going to start down here, and I'm going to notice that 15 over 3, both of those things, both those numbers can be divided by 3. So 15 divided by 3 gives me 5, and 3 divided by 3 gives me 1. So this ratio turned into 5 over 1. Next, over here, 16 and 2 can both be divided by 2. 16 divided by 2 is 8. 2 divided by 2 is 1. Now, right away, before I even get to this third ratio, I notice that I have one ratio that turned into 8 over 1 and the other ratio that turned into 5 over 1. Those ratios are not equal. I don't have to worry about trying to reduce this one. I know right now that these 3 ratios do not all equal each other because the last 2 don't equal each other, so they don't all 3 equal each other. And so that tells me right away that no, triangle ABC is not similar to triangle XYZ because the sides are not proportional. And remember, by the definition of similar polygons, if 2 polygons are similar, their sides have to be proportional. I know right now that these sides are not proportional, so that is enough to say that these 2 triangles are not similar. Now let's move on to this third example here. It says, in the diagram to the right, if triangle XYQ is similar to triangle XZP, does it follow then that triangle XPQ is similar to triangle XZY? So what we have is, first of all, we know that there's a pair of similar triangles. They're overlapping triangles here. We know that those are similar. And the question is, does that give us enough to go on to say that these 2 triangles would have to be similar? Well, let's start out and let's just investigate what we know if triangle XYQ is in fact similar to triangle XZP. If those 2 triangles are similar, we would know that angle X and angle X would be congruent, which would make sense because that's going to be this same angle up here. It's going to be congruent to itself by the reflexive property. We would know that angle Y and angle Z in those 2 triangles would be congruent, and angle Q and angle P would be congruent. But more importantly, we're going to know that there are 3 ratios that I can set up that would be equal. The ratios of the corresponding sides between these 2 triangles would all be equal by the definition of similar polygons or similar triangles. So let's go ahead and write those out. We know that XY over XZ would equal XQ over XP, and that would equal YQ over ZP. So what I just did there is I just used the similarity statement to pick out the corresponding sides, set each of those corresponding sides into a ratio, and said that they all have to be equal to each other. Now the reason why that's kind of interesting is that I might notice that two of these ratios involve sides of these two triangles that I'm trying to decide what are they similar or not. And so you might be able to tell which two ratios involve sides of these triangles. Well, look here. XY is a side of triangle XZY. XZ is another side of triangle XZY. So this ratio right here actually has two sides of triangle XZY in it. Then XP and XQ are both sides of the smaller triangle in this possible similarity. So this ratio also has two sides of one of my triangles in it. So if I just kind of bring those down here and say, well, I know that according to this statement up here, I know that segment XY's length and segment XZ's length as a ratio equals XQ over XP in a ratio. Now this is almost a statement that can be really useful to me, but it's not really, because in the SSS or the SAS similarity, what we're really looking for is ratios that compare a side of one of the triangles to a side of the other triangle. And these ratios compare sides of one triangle to each other, and this ratio compares sides of the smaller triangle to each other. So these are both small triangle sides. These are both like big triangle sides for these two triangles that we're trying to prove similar. But if I remember back to what we learned a few lessons ago about proportions, we learned that we are allowed to switch these two terms, what we would call the means in this proportion right here. So we can reverse where those are, and we can say that xy over xq would equal xz over xp. And now look at that proportion, because that's more along the lines of what we're trying to do when we're using SSS or SAS similarity. Because I have, in this first ratio, I have xy, which is a side of the bigger triangle that we're trying to look at in the similarity possibility. It has xy over xq, which is a side of the smaller triangle. The second ratio that we now have has xz, which is a side of the big triangle, compared to side xp, again a side of the smaller triangle. So this statement right here is actually a statement saying that two sides from this triangle are proportional to two sides of this triangle, or that corresponding sides between these two triangles are proportional. If we could say that the included angle between this pair of corresponding sides, the included angles that were congruent, that would be SAS similarity. And if we look over here, we might realize that the included angle between all of these sides is angle x, which is of course congruent to itself by the reflexive property. So we have a pair of angles that's congruent, and we have over here the included or the including sides as proportional. So we can say that yes, triangle XPQ is similar to triangle XZY by side angle side similarity. We use this information over here from the given similarity, the fact that these three ratios were all equal to each other because of this similarity. We pulled out a couple of those ratios that involve sides of these two triangles, and we used a little mathematical trick to flip-flop two of the terms, and it turned into a comparison of one set of corresponding sides to another pair of corresponding sides. And we know that those ratios between the corresponding sides are now equal, meaning that the corresponding sides are proportional, and we have an angle between them that's congruent, and that's what SAS similarity wants us to use. So yeah, these two triangles are similar if these two triangles are similar. Now the last thing we're going to do in this lesson is we're going to take a look at a two-column proof that uses one of these theorems. And so we have this diagram, and what we're told in this diagram is that segment CE, right here, over segment CB as a ratio is equal to the ratio of CD over CA. Now hopefully you might notice right away that what this statement up here in the given information is giving us is it's giving us a pair of corresponding sides as a ratio equal to another pair of corresponding sides as a ratio, meaning this is telling us that two pairs of corresponding sides between these two triangles are proportional. Moreover, we might notice that the angle that's between those pairs of corresponding sides is angle C. It's the angle between the two sides for the smaller triangle here, triangle DEC, and it's also the angle that's included between the sides that we were looking at up here for triangle ABC. So we actually have, based on this information and this reflexive property congruence right here, we have side angle side similarity that would prove that these two triangles are similar. So this looks like it's going to be a pretty straightforward proof. Let's go ahead and write out our statements and reasons. Statement number one, we'll use the given information. Segment CE over CE's length over CB is equal to CD over CA, and that is given. The next piece of information, and there's our sides, right? There's our proportional sides. Our next piece of information, maybe I need to do this. Maybe when I'm doing these proofs, instead of writing that off to the side out here, let's see, we can say that this is one pair of side lengths in a ratio equal to another pair of side lengths. So I have my two S's there. I also know that angle C is congruent to angle C by the reflexive property. There's my pair of angles that I need. So now I notice I have two S's and an A, and the angle pair is between these corresponding sides up here. So, like we talked about already, that's enough to say that triangle ABC is similar to triangle DEC by side angle side similarity. Pretty straightforward proof using side angle side similarity. Okay, so I hope this video helps you understand the side angle side and side similarities a little bit more. We'll see you next time, hopefully.